I think you should start, people will start quickly. So, this is the last day. The lecture studies. So, and Ceren, who's now feeling much better, will give the second lectures. Okay. You have water and stuff ready for yourself?
Yes.
Okay. Go.
Okay, great. Yeah, good morning, everyone. Last time we talked about, like, I posed these questions, how to make one, and that's and it was particularly challenging because we're talking about the conversion from reversible and linear function. And my reversible here, we define that, for example, since we're talking about a closed static quantum system, the state is going to be always pure. Okay? So that we need to calculate the time, and we will always find it. So this is really important. Question is how can we have like this every increasing entropy? When it goes to the linear part we're going to talk about. That's the part that we're going to connect hopefully this lecture to the random matrix theory. That is the modern quantum theory. And we said for the equilibration, like the word it happens if our observable expectation value in time is close to some equilibrium value for most times. And we put some like definitions and we even like look at some theorem and we'll test it on the board. So just to remind you, there were a few important notations. So the eigenstate expectation value, right, is the for eigenstate. And then the sum observable that we have here and also observable. Eigenstate occupation numbers defined as CM alpha squared, where the CM was the overlap of the eigenstate with the initial state. Okay. So a little bit on a visual level, something that I didn't do last lecture, but I thought like this enough. So if you have an aspect, you have energy, for example, you're going to write down the expectation value, and let's say it's like, it will never be like a nice clean line. It's going to be pretty cloudy, but overall as an envelope, if it's, let's say it's moving this way, okay? And then I can say that the occupation number will always be a distribution on the eigenvalue. Then your window into the element function. So that means whatever is going on, the dynamic is going on in the impervious. And then from here, we had also talked about an effective dimension, which is also related to the app, right? So related to initial space, this part is related to initial space, and this part is related to observable. So it's very clear two important spaces we talk about when we talk about equilibration and indeterminate space. Okay, and then the effective dimensions came out to be important when we talk about this theorem, which was bounding the fluctuation around that equilibration value. Okay. So, but now we're going to talk about thermalization, which is a different thing from an equilibration in quantum many-body dynamics. So why? Because a system can equilibrate, but if the thermalization happens, the equilibration value has to be predicted by a statistical ensemble. And if we're talking about a closed quantum system, then the statistical ensemble has to be microcanonical ensemble defined in a narrow energy window. So that is the eigenstate thermalization hypothesis. Okay, let's read it. Eigenstate expectation values of a large interacting many-body system in a narrow energy window around the mean energy is equal to the microcanonical thermal average of this observable. So then we can write down the microcanonical density matrix from the eigenstates staying in this narrow energy window. Okay, so this notation here means we're just coming over
in this narrow energy window, and in here is the number of states that remains in that window. Okay, and here's some properties about that window that you can see it's a narrow around a mean bar. So we're going to talk more about like some more rigorous statement about eigenstate thermalization hypothesis, but what does it mean? The essence of this hypothesis is actually like just one eigenstate alone in this window can predict the long-time behavior, long-time statistical behavior of the quantum system. So it's very powerful in that sense. And we're going to come to why this is the case. And it's going to turn out to be related to the structure of these eigenstates. Okay? Because they can actually encode these long-time properties, equilibrium properties of the Hamiltonian, these states are also called thermal eigenstates in the literature. Okay? But keep in mind, these are pure states, right? These are not density matched. I mean, these are not mixed states. Okay, some important references about eigenstate thermalization hypothesis. I'm going to mention some of them on the go. Okay, so there are two notions of ETH, and the strong notion is the most well known, and that's this is basically just a more rigorous way of writing it down what we just said in the hypothesis level. Okay, so there are two criteria, and ETH holds if these two criteria are satisfied. The first criteria is the diagonal part of the eigenstate expectation values change smoothly with the energy eigenvalues. Okay, so for example, if we have, let's say, if we have this kind of an eigenstate expectation values, and we choose, you know, somewhere in the middle of the spectrum, typically that's what we do. We choose a narrow energy window, let's say these red ones, and we look like, you know, how the eigenstate expectation values act in this between here. So as I told you, you know, in a second ago, you will never have like a clean line. Okay, it will be like cloudy. But typically what we expect is we do a system size scaling, this like basically this width here is gonna get smaller and smaller, and it's gonna approach to a certain value. So again, like the first part is like the diagonal elements is gonna change smoothly with the energy eigenvalues. Now there's a second part which says that the off diagonal of the eigenstate expectation values should be much negligible compared to the diagonal part. Okay. While at the same time the off diagonal parts are a smooth function of energy differences between dm minus dm. So overall, we can actually mathematically write down eigenstate thermalization hypothesis this way. Okay. So it is really a statement on the eigenstate, you know, the observable behaviors. So the first part here, the first criteria, also called diagonal ETH in the literature, and then the second part called off diagonal ETH. The first time that this was actually written, it was in Ceren Dag's paper from 1996, so almost 30 years ago. So this been like, and still ETH is a like active field of research. So ETH is going strong for 30 years, so far. Okay, so let's see. Okay, let me just give a little bit more detail here. Right, so I just wrote down an equation here. So first of all, the mean energy. Okay, let's first look at this part is clear, right? So you have some mean energy and you have your observable. And we said this is going to be a smooth function of the energy. Okay. And then the second part of the part, again, n is a smooth function of the both mean energy and then the differences here. And importantly, here's this Rm, which is basically a real or complex random variables drawn from the Gaussian ensemble. So this part is going to be really important for us. This is where actually we connect the random matrix theory, which I'm going to define. Okay. So an important thing about ETH, like one of the important things about specifically the strong form of ETH is that the statement that, you know, the dynamics is independent of the initial state. Okay, So, and there is a way to see this, starting from our mathematical relation and just focusing on the first criteria. We can expand the eigenstate expectation values around the mean energy. Okay, and the mean energy can be simply written in terms of the eigenstate occupation numbers, right? And then the energies here, the eigenstate energies. And then if we expand this, Taylor expand this. Okay, normally I was gonna do this here, but because I am running late, now you're gonna do this yourself. But it's really simple, right? It's just a Taylor expansion, and then what you're gonna do is like you need to just like write basically the okay, let me see here. The point is basically write down this NMM here, okay, which is something that we did in the last lecture, and then just carry out the calculation, and you're gonna see the first term, the first order term is gonna disappear. What's gonna happen is like you're just gonna have like this 0th order term and then the 2nd order term here, okay? And that's actually gonna give an important result. What that would say is under this condition here, okay, the expectation, the mean, basically the mean value of your expectation values is gonna just depend on the mean energy, okay, in your narrow energy window. So even in your narrow energy window, like, you know, there is basically no dependence on the specifics of the eigen energy. It's just really dependent on the mean energy. So it depends on the energy density. So that is a statement of that ETH is independent of the initial state. And then this thing here, you can, as I said, it comes from the map. And you can see here, this is the second derivative that comes from the Taylor expansion, and it gives a sense actually of how big the window, energy window you should choose, okay? Because that's the delta E here, the energy window. And also it gives you a sense of like how smooth that's like N should be, okay, in your energy window. Okay. All right, so I'm gonna skip this because this is just basically numerically how we like more rigorously prove ETH. If you're curious about it, just ask me at the end of the lecture, okay? It's not very vital. If you're doing ETH research, it's really important. But let's come to the weak form of ETH. So ETH holds in its weak form the first criteria for typical eigenstates in the energy spectrum of the diagonal parts of the eigenstate expectation values change smoothly with the energy eigenvalues En. Okay, so the only change here from the first one is the typical eigenstates. And then the fraction of non-terminal eigenstates vanishes in the system size. So the important thing with the ETH, your your eigenstate expectation values might not be completely smooth throughout the whole spectrum, okay? You might have actually some non-terminal states in your spectrum, but what's important is that their numbers are rare. They're rare, their numbers are low compared to the rest of the Hilbert set. So then what we can talk about is fraction of the non-terminal eigenstate compared to the terminal eigenstate. So if this is vanishing in a system size, then there could be non-terminal states existing, but they are vanishing in a small part of the spectrum and semi-rare, and it requires actually like sorry, this is wrong thing here. It requires fine-tuning basically in order to access these things. Okay, so but that doesn't mean that the ETH cannot hold. For example, if you're like, you know, if you're choosing an initial state, which is typically the case, and it's overlapping with the terminal states, then you're gonna see ETH holds. And you're gonna see terminalization and equilibration. Yes.
Very good question. Whether thermal eigenstate or non-thermal eigenstate, but again, I guess it's
Yeah, so one thing is from looking at like the quantity, and especially the last part, the it connects to the random variable. I'm gonna show in a second, but this, ETA and everything together. It's like this combination of, daily random. That's where the random comes from. I like to show you this, example of a weak, ETA. Probably one of the most like prominent examples nowadays is the quantum many-body stars. Okay, so if you ask me what is a quantum many-body star, literally it's like these non-thermal many-body states embedded in an otherwise thermal chaotic spectrum. Okay, their numbers are low. Like for example, if you look at these plot here, it's like an IS expectation values of some observable. You'll see some colored ones here. These are actually quantum many-body star candidates. Okay, and for example, you can see that their numbers are low compared to the rest of the Hilbert space, the dimension of the Hilbert space. Then you can ask, okay, like what's the importance of these? Like they're like such small, like their numbers are so small. Why are they important? Here's the reason why they're important. These states are actually low entanglement. They have low entanglement. Okay, so they basically low entanglement entropy. Having low entanglement entropy, if you prepare a state in the lab, likely it's going to be a low entangled state. Typically, actually prepare product states in the lab, and then a product state that you prepare will most likely actually overlap with these low entangled states. Okay, and that's the reason, for example, these states were for the first time discovered in lab. Okay, not this particular model, but like a model for a Rydberg atom array. Okay, and literally like they just prepare their like up down nail state, and they do a quench, and they basically find well-defined isolation. Okay, you don't expect that in a typical quantum many-body system. You expect thermalization, because most of the states are thermal. You don't expect to just like go and overlap with these special eigenstates, but they did. And that was, partially perhaps like a rule of thumb is that because we prepare, we prepare product states. And then you go and like choose a kind of special state. Okay, so take-home message, there are two notions of ETH, strong ETH. All initial states can thermalize the system, whatever initial state that you prepare. While weak ETH, most initial states can thermalize, but not all. Okay. All right, so what time is it? Great. So going back to the ETH ansatz, okay. The second part we were just actually talking about, that is our connection to quantum chaos, random magic. So I'm going to actually give a more clear definition of random magic theory. But let me just go through a little bit what was going on in the literature. Okay, so as I said the first time, Shiniki put this form, put forward this ansatz, and he didn't drive it, or he didn't actually prove it. It's a hypothesis, right? But what that means is you have a system, you go check whether it's satisfied or not. So that's the reason why you can find ETH to be satisfied or violated. Both of them are exciting results, basically. But what he said when he put forward this form is consistent with the behavior of a classically chaotic system after its quantization, which is random matrix theory, where random matrix theory comes out. And there is random wave conjecture for the energy eigenstate. So he basically, argued, his way from the random matrix theory. So this is our connection, actually, how ETH is connected to RMP, random matrix theory. Okay, so you can ask me what is various random wave conjecture. I'm not going to get into too much details, but what it is eigenstate coefficients of quantum system, again with a chaotic classical limit, in a generic basis are independent Gaussian variables. That's basically the essence under the very random wave conjecture. So what does that mean? Okay, so if you're right on here, what you're seeing is a plot of a system. Okay, there's multiple lines here. What they are is not that important. Just keep in mind that as we increase this px variable, the system is becoming like, let's say, more random, as we see from the plot. Okay. What it's becoming is actually your that's the integrability breaking parameter. Okay. So you're making your system more and more, let's say, typical quantum many-body system as you increase them. So what you see here, if you just focus on this large red here, that it is actually it's following this black line here. Let's talk about what this is first of all. So you have your energy window, and in this energy window, you look at the eigenstates. You write down a projection operator from your eigenstates, and then you look at the diagonal elements of it. Okay, and multiply it with the dimension of the Hilbert space. And those are going to be your eta vector. Okay, you do this for all the states in your energy itself, and then you write down a histogram. Find a histogram out of it. So what it's telling you is actually how the eigenstate elements, the coefficients, are distributed. And they're distributed according to what's called Porter-Thomas distribution. That's what we're seeing here. And that's the Porter-Thomas distribution for it. It's one of the important distributions coming from the quantum chaos. So this is actually linked to the chaos in ETH, in eigenstate normalization. We expect this to happen if ETH holds. Okay. All right. What is this random matrix theory? All right. Yes.
Why is it?
ETH is a hypothesis. It's actually from from this ETH ansatz, it's sort of possible to see it. When you look at the second part here, this function is not that important. It's just more information in ETH. But here there's an RMN, which is random variables coming from the Gaussian distribution. So this is actually our connection to in the mathematical level, it is our connection. And this is the reason why Ceren in the first place wrote this on the he was coming from the random matrix theory.
Next slide.
This is the first time that this distribution was used. I think that was in the Porter and Thomas's paper. I think that not really this paper, but I would recommend them to go to the Hayek paper, Hayek book. There are two main books in the RMT. One of them is Quantum Signatures of Quantum Signatures of Chaos. The other one is Random Matrices by I can't. Okay, it's gonna appear in the other side. Mehta, sorry, yeah. So in these two books, basically, you can see all these distributions coming out. Okay, yes. So eta is you have a window, energy window, right? And you take your energy eigenstates there, write down the projections from those, take the diagonal elements in that. Right, so basically what it's getting is the coefficients of your eigenstates, right? No, this is a statistical property, right? So you need to just get all of them, not average or something. Get all of them because you want to get a clear like histogram here. You typically cannot do that with just one eigenstate. But if you did, like if you, let's say you had a very, very, very large like system, somehow you managed to get the eigenstate, maybe you can do it with Lanchos, algorithm with the exact diagonalization. You should be able to see this. The just single eigenstate should have this.
How do you choose the bits for the integration?
How do I choose?
Yeah, the bits, because that's what is the effect, right?
No, in principle it shouldn't, right? So you need to make sure the bin size is not like the, is not affecting what distribution you're getting.
How can it's, how would you choose this fitting? Another, not another one.
If you did choose another binning, I don't think you will like, get, you shouldn't be getting a significantly different result. I don't know how I can answer this question, yeah. Okay, great, okay, what is random matrix theory? So we talk about like this part a lot. Now let's talk about this part. The Schrodinger equation is linear. So how does chaos come out? Like, right? Okay, what is classical chaos? We talked about this a little bit in the first part. Really the important thing is sensitivity to perturbation. I would say that's like the key element. Like if your system, classically, I'm talking about a classical system, you have a phase space, you have like trajectories. If your trajectories are sensitive to perturbation, exactly that's how we define Lyapunov exponent anyway, right? So and we just go back here, and if you try to like apply the same reasoning to a quantum system, the first thing that we see, like let's say our trajectories are our states, and we have like let's say like just two like different states from each other. Initially, their overlap is this, and at some time t, their overlap is going to be still the same thing. It's not going to change. That's something that you can just like write down with the evolution operator and show it to yourself. So this is basically not going to help us. This is not intuition that we're looking for here when it comes to chaos in quantum systems. But then the intuition is still connected to the sensitivity, the perturbation. Okay, so this is how Wigner started to think about. So what Wigner said that Wigner was working on like the understanding the nuclei, like the large nuclei energy eigen levels and eigenstates. Okay, and he said let's focus on the statistical properties of the energy levels of these complex things, right? These like nuclei, instead of trying to predict the exact energy eigenvalues and eigenstates. And then he said, let's look at small energy windows where the density of states is constant. Then the Hamiltonian in a generic basis should look like a random matrix. So that was really his like, let's say, genius insight here. If this is the case, like this is basically an if state, right? If this is the case, then he said, okay, if I then study the statistical properties of random matrices, because they look like random matrices, while preserving the symmetries of the Hamiltonian. Now we can learn about the statistical properties of energies and eigenstates of these complexes. And it turned out it's correct. Okay. I'm gonna actually first show you this. It turned out its correct part is an experiment. Okay. So that was the theory part. So the why that turned out to be correct is related to basically, and when you look at like the experiment, when the people did the experiment on like the nuclear data, basically, they found these energy eigenvalues are distributed according to certain distributions, and that's really what you expect from the random matrix theory. So that was the first like evidence that like random matrix theory is really the correct way to go here in understanding the nuclear energy data. Okay, now let's go back like understanding random matrix theory. What is random matrix theory? Sorry, I need to drink water. Is there any questions so far? Okay, so the nice thing that we can understand RMT with just 2x2 matrix. So let's say we have a Hamiltonian matrix with epsilon 1, epsilon 2, and V just drawn from the Gaussian distribution. Okay, they're just random numbers. If you just diagonalize this, we will get the energies simply this way. It's just a simple calculation. Here, if there is a time reversal symmetry, then V is equal to the conjugate for the Hermitian. This is called Gaussian orthogonal ensemble, and if not, then this is called Gaussian unitary ensemble. So it's just a different symmetry that we can actually put into this random matrix theory. So the important thing is normal distribution for a single random variable. If you use this normal distribution for a single variable, we can get the joint normal distribution for 3 random variables if we want to write down a distribution function for the energy spacing. Okay, so this S here is the energy spacing. So if we calculate the energies, it's just E1 minus E2, 2x2 matrix. After writing this, take the integral. Okay, and then you will see actually a distributions coming out like from those integrals. Okay, 2 distributions I'm just telling here does relate to their symmetries. If there's a time reversal symmetry, then you will get this distribution. If there's not, then you will get this one. We say these orthogonal and unitary. So, but what's the important thing about these distributions? Let's just look at them a little bit. The first level repulsion. Okay. That means the probability of having an energy separation of omega is equal to 0, which is the spacing, energy spacing in your system is 0, while the probability decays as a Gaussian at large energy separations. So both of them have these properties. And now going back to these plots here, basically what you're seeing here is this one, not this Poisson, but these nuclear data, how it's distributed according to Gaussian orthogonal. This one here. So basically what we did right now, very quickly, is I sketched here how we can get these distributions from 2x2, and how actually these distributions also apply to just larger than 2x2. Okay? We can have n by n, and these distributions will be coming out. Okay. Let me also mention here why these people are comparing the Poisson distribution. So first of all, if you have this kind of distributions, an important thing is that what it tells you, this level repulsion, the thing under level repulsion is the correlations between your energy level. That's what it's like, what it's encoding here. The correlations between your energy levels. And particularly these plots here are showing the correlations between nearest energy levels. Okay, nearest spacings that we're looking at. What Poisson says is, Poisson distribution says, if the system's energy levels are not correlated with each other, then it should have actually shown Poisson statistics. So this is a great way for us to actually check this in any system, right? Right now, of course, this is not like a many-body system, but the idea behind this is so generic that you can actually apply to others. And in fact, that's where this question came then, okay, random matrix theory, only nuclear energy levels. Is that the case? Are there other systems that can actually show this? This was the question at those times, apparently. And it's a famous conjecture, BGS conjecture, what's called. They said no, actually, they will appear in some other complex systems too. And they said it is found that the level fluctuations of the quantum C nebulars are consistent with predictions of the Gaussian orthogonal ensemble or random matrices. And they say this reinforces the belief that level fluctuation laws are universal. Level fluctuations are what we were just talking about, right? Level statistics, the correlations between energy level spacing. And what is a quantum C-modular? It's just like a particle. This is a single particle problem. It's a particle in a stadium potential. Okay, subject to a stadium potential. It is really like the paradigmatic example of quantum chaos. That's what people start to learn about the quantum chaos in based on these basic systems. Okay. Of course, okay, this is still in a quantum many-body system, and that's what happened in the last, following years. Not really immediately, but, like starting from probably 2000s or something, people started to actually look at whether these distributions also come out for the level spacings, energy level spacings of the quantum many-body systems. And for an extensive list, you can check like this review paper here. Was there a question?
I just wanted to elaborate on the potential in the block. So you have a single problem particle, and then you say
It's not a stadium potential. I don't know. It's not a really nice stadium. Okay. Let me find it will be helpful. Okay, give me a sec. Ah, okay. Can you see this? This is basically, right, this is just an eigenstate right now on that particle subject to stadium potential. The quantum particle subject to stadium potential. This eigenstate is not chaotic though, okay? Let's just not get in there. Okay. All right, I have 22 minutes. So what I want to do, actually, I want to tell you here, like, how like the interest in random matrix theory got renewed in the last years. I'm not going to get into details because I don't have too much time. I want to actually give you an example of how temperature emerged in a closed interacting quantum many-body system. But before that, let me say, so the interest recently in recent years is in terms of capturing the correlations, like the correlations in these the energy separations, energy spacing beyond the nearest neighbor. So what we say long range correlations in the energy eigenlevels. So and a way to capture that is called like spectrum form factor. These are again actually coming from random matrix theory, but now like we're finding like certain universal modifications to these to these like random matrix theory quantities, just because the systems are quantum many-body systems. This is just a recent research area, which I'm not going to come in here. Maybe I can call it up. All right, so I'm going to close with answering the question that I posed. How does the temperature emerge in a closed interacting quantum many-body system? So this is an underappreciated work in the literature that I want to highlight here. I came across this in the beginning of my PhD. And that was the time that I was transitioning from quantum thermodynamics to the quantum many-body systems in general. And I was thinking how one could actually connect these things. And given my interest in the ETH at the time, I was thinking, well, like really the interesting thing would be like, how do we make a quantum batch, like finite system quantum batch? And this paper came out. And that's what I want to actually go through with you, just some main results of it. And if you're interested, you can go to its like, more theory sections. I just want to give an example of how ETH can be applied for quantum thermodynamics from quantum thermodynamics perspective. Okay, so this work has two-band double well model for cold atoms, okay? So it's a double well, you just have double well right and left, and that is encoded in this index R here, and it has also a two-band, okay? That's encoded in this index R here. Let's go over the Hamiltonian. So you can see there is a hopping. It's a hopping between the wells, double wells, R prime. So this is the hopping between left and right. And then you have interactions. You have interactions at both sides, both R and L. It's an on-site interaction. It's both bosonic. Right? And then you have chemical potential term, okay, which can be fixed with whatever trapping potential you have. And then importantly, you have these interband interactions. Let's look at them. There is a density interaction between L and L. Okay, so between your bands, the interband, right? And each right and left well. You have also these tunneling assisted, density assisted tunneling, I think, interactions, or no, correlated hopping interactions, right? So again, like, fixed R, like R or the right or the left well, but then you have L prime here, again, interband. You have this kind of Hamiltonian, imagine, okay? And then the first thing that you want to do, you want to check whether ETH is holding. And for this, you have a particular observable, okay? We can talk about that maybe in a bit. Anyway, so you have an observable. You expect this observable to be the one that connects to your subsystem, okay? Because right now what we're trying to do is that. And you look at the eigenstate expectation values of this observable. You can see, like, it has some sort of distribution to it. It's more cloudy here and then more clear here. So we're going to choose this part here because we expect to see ETH would probably hold at this part. But for example, if you did put your, the energy density, you wouldn't expect because it's too, like, it's not really because what was the first criteria? The eigenstate expectation value diagonal elements has to be a smooth function of the energy. So that's what we're looking basically here. So the smooth function, okay? This is, for example, a good example of, let's say, perhaps a weak ETH. But I would say probably this is even weaker than that because there are so many of them. I'm not sure. This is not something that is paper checked, but anyway. So after doing this, we can, and also an important thing, okay, so this inset, what does it show? It shows the second criteria. Okay, it shows how does the off-diagonal elements of the eigenset expectation values are distributed. And they really show, like, it looks pretty Gaussian. So, and they're doing this around this energy here. The part that if they did this here, they wouldn't see that, right? And that's an important part why ETH is going to hold at this part and not at this part. Okay, great. So this is a good, like, place where ETH holds. Then what we do is we write down the microcanonical ensemble density matrix, just like what we defined, right? And now from here we can calculate von Neumann entropy. Keep in mind now, okay, it's going to be non-zero. Why? Because because it is actually, it's not a pure state anymore. You're doing an averaging over many eigenstates. Then from the entropy that we find, you can actually calculate an inverse temperature. So this is what it plots here. First of all, here the inset is the entropy plot with respect to, okay, so you're looking all the way here from page 5.5. And then here's the beta, the inverse temperature. So basically going through these steps, you're able to see how temperature comes out, okay, in this. closed interaction quantum system. Yes,
So what was R sub K in the inset on the left?
this one, that is that's basically remember the ETH ansatz? Right, so we expected the off-diagonal elements of the eigenstate expectation values to be distributed according to random variables, Gaussian random variables. So what this is plotting is really it's taking like, the eigenstate, and it's looking at like it's taking the eigenstate expectation value at a particular energy, and it's looking at the how off-diagonal elements are distributed. Okay. It is basically looking at the off-diagonal elements with respect to the energy differences. That's the second part of the equation. And they're showing it's distributed according to Gaussian distribution. Okay. So you can ask, okay, then this is the bath. This is the finite size ETH bath. Does it really thermalize? It does actually. So they do this numerical experiment. They have a two-level particle. They say we have a two-level particle trapped in the double potential, in this double potential. Then you can write down the Hamiltonian of this two-level particle this way. Okay. Now you have these different the annihilation creation operators for your particle. Okay, keep in mind, and it goes from 0 to 1 because you have like two bands. Okay, your bath has two bands. Okay, and the epsilon 0 here is the energy of this particle. And then you can write down an interaction Hamiltonian between your two-level particle and your bath Hamiltonian in your bath system. Right, and then you can see this is actually happens through this particular interaction here. Right, G, it's just proportional here because there were a few other things. This is the most important thing. Okay, then what we do is we say, let's start the system, the subsystem, the small two-level particle is not entangled with the bath. Okay, so they basically initially it is going to be like you can write it down as a tensor product. Okay, the state, the overall state, you can write it down as a tensor product of the two-level and the bath part. And then they choose two different initial states, okay, for the two-level system. One of them is either the two-level system is in the ground state, or the other one is the superposition of these two bands, basically. Okay. So really the important thing here is that you need to make sure when you're writing these things that your two-level system and the bath should be able to exchange energy. Right? If you can do that, then you know that there is a way for energy to flow. Okay. So, and then they look at, after this, they basically look at this is the entire system, the entire system state coming from like both the two-level system and the bath. And at some time t, they trace out the bath and look at like, the density matrix of this two-level system. So the expectation is if this is really a bath, then we should see the temperature of this two-level system should approach to the bath temperature. Okay. So take me here. Okay. So first of all, like rho relaxes to a eternal state after some time. That means your coherence elements of your two-level system should be 0, expectedly, right? Because it's thermalizing. And then one finds the qubit temperature through this. Okay. So from the diagonal ratio of the diagonal elements, this can give us this qubits two-level system temperature. And this is what you see in this plot. Okay. What you see here is rho 1, 1 and rho 2, 2. Okay, for example, first of all, what you see here is rho 1 and rho 2, 2, like this diagonal elements of your qubit density matrix is approaching to the same values, no matter what the initial state is. So this is an important thing about thermalization. The memory of the initial conditions is gone, and that's what we're seeing here. if we did this actually, say like, at a different, at a different energy density where I showed you ETH didn't hold, right? Actually, this one. We did it somewhere here, that we expect ETH not hold, and in fact, one can show it doesn't hold, right? Then they actually see that it's not the case. Okay. And these are basically like again, the same kind of thing. They're looking at the elements of the density matrix for different initial states, and you see that they don't come close together. So basically, there is really no back behavior here. There's still initial memory held by the qubits, even though it's connected to this large, like, two-band double weld model. So it's basically not terminalized. Okay, so this was the example. And is there any questions right at this point? You see time? Okay. Yes.
Is there any dependence on the number of particles in the
This is a very good question. As I told you, this is an underappreciated work. You can go and check that. So that means people didn't really follow up on this. But I think an interesting question here, yes, what is the dependence on the size of the bath, right? So these are really, this is, like, to my knowledge, this is the first finite system ETH bath that can thermalize a qubit. So now the questions to ask, like, if I did have 2 qubits, would it thermalize it too? If I did have some like correlations between them, entangled, like what would happen? Would that change anything? At the same time, one needs to look at how the temperature of the bath is changing. It could be changing, right? It's still finite bath. So then you can find the conditions, for example, what should be the size of the bath so that we don't see an appreciable, the change in the temperature of the bath. There are many questions to ask here.
There's a paper I read which went up to a Hilbert size of, you could say 44 qubits.
40.
But you did exactly that. So part of the bath and the other part is the qubits, and he checked. He went up to 44, and he checked really thermalization, 1 and 2 qubits.
Okay.
So he's a unit, so he needs huge computers. 2 to the power 44 is quite high. This is probably the largest classical calculation that I know.
Yeah, 44. I mean, I cannot do 44.
So basically what it does, it takes, builds a bath up, spins, some interactions, and then singles out 2, and he basically checks the same.
Okay. This is a new work, or when is this from?
Can be because people, but he's a new, so.
Okay, I'll check it. 44.
That's the largest equal to. You should think, okay, the 20 is million. So
Yeah, 20.
40 is the million times a million. So 44, that's a maximum. It's almost all the memory. So limited by memory.
Yeah,
memory
totally. Yeah, right now, if you, for example, do this on your computer, you will see like, you can do easily like 14. You need to wait for 16. You might want to start using like a cluster for 18. And then you need to start like making your code more and more and more efficient with the others. I don't know how you do 44. I don't.
So he's in where there's a huge computer center, he has resources.
I heard Google people can do those numbers. Google Cloud apparently has some sort of like very specific resources. Yeah. Are there any questions? Okay, so I have just 5 minutes, I suppose. Yes. Yeah, I think so. It's. Yes, yes. So actually, I want to show this too before closing, so that you know that what we're talking about is not just on paper, not on theory. this is actually the one of, okay, this is not the one of, it's the first, the quantum simulation experiment of quantum thermalization. So here they have, it's a little small, of course, here, but they have basically, two copies of a chain, okay? And by doing like a certain protocol on this, which I'm not gonna get into details, they can actually measure Renyi entropy. Okay, you can measure actually in a cold atom system any Renyi entropy. If you just have 3 copies of your 1D chains, you can measure the third Renyi entropy or whatever. So if you have these, you can actually bounce to the von Neumann entropy. So or basically, capabilities, to my understanding so far, is that measuring von Neumann entropy in lab is really putting bounds through the Renyi entropy. But anyway, we can measure it, and it was really like a seminal work, and opened up so many things. So it's from 2016. And you can also see, like, in this paper, how they're looking at subsystem thermalization on top of, like, what we talked about, isolated closed system thermalization. There's also subsystem thermalization, which is actually more intuitive for us. If you're talking about just a subsystem of a larger system, there are actually very powerful theorems, which, because I didn't have time here, I didn't talk about. But there, for example, we do see, like, when you define the entanglement entropy, you can very clearly see how entanglement entropy increases over time and saturates to a certain value, which is related to the Hilbert space dimension. So, and here what they are showing is actually, they're looking at different partitions here. For example, they're looking at this middle part, and then this half of the system, etc. And they're looking at, how these systems, can be described by different statistical ensembles, and they see good, match with like different ensembles here. So there is, like, basically the evidence of thermalization going on in this, even like pretty small, cold atom system. This is other experiment I want to show, and that is like the first experiment that showed little statistics in a mini-body quantum processor, the superconducting processor, and it's superconducting qubits, and they basically show here, like, I think it was 9 sites and 2 excitations. So then in this particular case, for example, depending on where you're quenching to, you can see the Gaussian distribution coming up for your energy level separations, nearest neighbor energy level separations. And if you're quenching to some other part where you expect localization, then you see something more along the line of a Poisson distribution. That's an experimental evidence for that. All right. And here, basically, I like to close, and thank you for your attention.
Very much.
Yep, I would say typically that's what we expect to see. If you're seeing it's violated, it's exciting.
You understand why it was violated in the finite sense for example?
Oh,
It seemed to be violated.
I don't understand that. One needs to, like, look at that model more, particularly. One needs to look at, like, those cloudy parts of the expectation values a little bit more carefully, where it's coming from. It's not even clear whether that's weak ETH. Like, as I said, there's just 2 notions right now, but perhaps one could actually, like, enrich this a little bit more. There are always, like, cases in between. You might not have, like, just a few of them, but you might have a many still non-thermal states. So I think it's still, like, ongoing process, basically, for understanding.
also probably helpful to sort of think of setups where you could test these so-called strong and weak
That's right.
pH.
Right, there is not really too much appreciation of this different notions. And only the people who are doing ETH work, they know, like, strong, weak, they will separate things, they will try to understand things. But when it's like a little bit out, like the only thing becomes like, okay, let's go check for ETH. And then, yeah,
Here's something that we can sort of use.
yeah, right,
It's an opportunity.
right. Also,
Thinking.
let me know, like, when you look at the literature, most of the time you're gonna see like people just check the diagonal ETH and they were not gonna look at the off diagonal ETH. I think it's a little sloppy, but people don't think that way, I suppose. So. I mean, even I need to like give a fight like to my collaborators that look, we have to check all these things step by step, but it's a different thing to do an ETH research and then being just in quantum many physics dynamic and you just want to use ETH.
Questions? No, then let's take a short break. Thank you, Ceren.
Thank you.